Good morning, students. In this lecture, we will talk about plastic instability. So for the reference of this, you can read or go through chapter 5. So what is plastic instability? This plastic instability is very obvious, particularly when we are doing uniaxial tensile test. So when we see plastic instability and the uniaxial tensile condition, then we see that the load starts to decrease even though the strain is increasing. So we are talking as in terms of the overall component and not as the local stresses. Local stresses are of course increasing. So plastic instability relates to a condition of plastic deformation at which the deformation would continue under a falling load. So that is a, you can say, working definition. So usually we expect that for increasing deformation, we have to apply at least as much force as we were applying earlier. And in most cases, there would be increase in stress or pressure. But after the point of plastic instability, the required force or pressure would decrease. During tensile uniaxial test, the uniform elongation ceases. And why does that happen? Because the instability occurs at some regions which are weak or where there are some variabilities, and therefore the stress gets localized in that region. But as a overall, the body, if you look at it, the load is falling and the deformation keeps on happening. What is happening is that the overall, the stress is not being applied, or the elongation is not uniform. It's not happening throughout the gauge length. It's happening in the localized region. So during the uniform elongation ceases. So if I had to draw it, this is how it would look like, and something I have drawn earlier also. So this is our, in the uniaxial test, this is the dog bone, and probably this is the gauge length. So until the uniform elongation, or until before the point of instability, this whole region is getting deformed. But at the point of instability, there is some, because of some variability in the material, some particular region, there would be a necking that will have formed. And beyond this, the overall stress and deformation would be limited to this region. And that is where the load requirement goes down, even though the deformation keeps happening. So in uniaxial condition, this plastic instability is termed necking. Now, since the load starts to decrease from this point, it means that there must have been a region where the maximum amount of load must have been applied. And therefore, if you look at the load curve, then we can identify this point of instability by finding the region where load is maximum or where dF is equal to 0. So let me draw this to be able to appreciate this better. So let's say we are drawing the load versus elongation plot. Then it is at this point where dF is equal to 0 is the point of instability. Because even though your overall force is decreasing, but elongation keeps on happening. So let's try to understand this with respect to one of the simplest condition, which is the uniaxial tension condition. And let's assume that the material has a power law hardening behavior. So sigma is equal to K epsilon to the power n. Now we know that, let's say we are applying a load F, then in the gauge area, F is equal to sigma, where sigma has to be effective stress times cross-sectional area A. Now at the point of instability, we know that dF is equal to 0. But we know F is sigma times A, therefore we can write it as sigma dA plus A d sigma, and this should be equal to 0. And now if we rearrange it, what we will find is that d sigma by sigma bar is equal to minus dA by A. But then for uniaxial condition, we also know that because of the volume constraints, dL by L is equal to minus dA by A, which is equal to the differential strain. Hence, we can write this equation also as which means d sigma by, sorry, now we can rearrange equal to sigma bar. So this defines our plastic instability condition for uniaxial condition. Now let's put the relation which we know is sigma bar equal to K epsilon bar to the power n. So d sigma by d epsilon is equal to n times K and on the other side we have sigma bar, therefore this is equal to now when we put this together, what we will find is that epsilon bar is equal to n. So for a uniaxial condition, this is a very useful result. What it says is that if you know the if we know the power law hardening relation, then the n, the strain hardening exponent, n also gives you the uniform elongation value that you can expect in this material. Or in other words, if I were to again, let me go back and use this one. So this is the point. Only up to this point you get uniform elongation. That much we understand. And now this relation tells us that if this were to be sigma bar versus epsilon bar, then this is also equal to n. So this is a new information that we are able to obtain if we apply this equation. And it also means that if we have different materials with different power law hardening behavior, with approximately similar material, then we can say that as the n value increases, then the total elongation would also increase. Or so what we are saying is that as n increases, total elongation, actually first we should say only about the uniform and hence the total. And hence total elongation increases. So let me just draw this. So let's say we have 3 different materials of starting same type of dog bone. So let's say this were the dog bone starting for 3 materials where let's say n is equal to 0.1, 0.3, 0.5. Then what you would see is that for 0.1, at the end of it, it will look like something like this. For 0.3, the total elongation is expected to be larger. And for n equal to 0.5, it is expected to be even larger. So this is the schematic of what is the meaning of increasing n. So you can see that the sample thickness has become smaller and smaller, which means uniform elongation was larger, and also the total elongation is larger, which is evident from the total height of the sample that I have shown over here. So this is the implication of n equal to epsilon bar for the plastic instability condition. There is something called as considerate criterion. So from what we have already obtained, we can, if you are to plot the true stress versus true strain plot, so it will look like something like this. And at the point of plastic instability, if you draw the slope, then what it is saying is that this is your sigma, this is strain equal to 1, and this is the slope d sigma by d epsilon. So we know that d sigma by d epsilon is equal to sigma by 1. So this is geometric representation of what we have understood. And up to this point, if you look at epsilon bar, it will be equal to n. And we can also draw it a little differently. If we so let's say we are drawing the slope. So the slope is continuously decreasing. As you can see, the slope is continuously decreasing, which is represented by this. And this is the stress curve. So at one particular point, they will intersect. So there is slope equal to d sigma by d epsilon. This is sigma. And this is the point where instability or necking starts. So y-axis represents stress and also the slope d sigma by d epsilon. So this has the unit of stress units, and x-axis has strain units. So the condition for necking in a tension is met when the true stress sigma equals the slope d sigma by d epsilon of the true stress strain curve. So this is the true stress strain curve. So this is the condition where for the necking. So this is the point where necking begins. Another important point about n. So we see that n can have a range of usually of the range of 0.1 to 0.6. If n is low, then what it means that the work hardening rate is initially high, but the rate decreases very rapidly. I will schematically draw to explain it. But the rate decreases rapidly with strain. On the other hand, if you have n as very large, relatively large, then it implies that work hardening rate initially is low, but it keeps on increasing for very high stresses until high stresses. So initially it is less rapid, but continues to rise. So if I were to schematically draw this, this is how it would look like. So this is for low n, and for high n, this is how it would look like, assuming that it has almost same elastic constant. So this would be the difference between low n values and high n values. And it is clear why it should be so, because for high n it means total uniform elongation is high and total elongation is high. So initially it is less rapid, but it continues to high strains. On the other hand, for low N, you will have low uniform elongation as well as total elongation would also be low, and therefore it rises very rapidly, but then it decreases, saturates very quickly. So that is the implication of low N and large N values. Now let's understand this with the help of one example, which is also of similar type. Here it is given to you that the force condition is biaxial in nature and it is balanced, meaning both the forces are same. So it should have, if it were sigma 1, this is sigma 2. Then what it is saying is that sigma 1 is equal to sigma 2 and sigma 3 is equal to 0 because it is biaxial. Okay, so using von Mises condition or von Mises criterion, gives sigma bar equal to sigma 1 or sigma 2, whatever, because both of them are equal. Now, since it is symmetric, therefore epsilon 1 is also equal to epsilon 2, and it is a plane strain, a plane stress condition. Therefore, the third one will have to be such that the total volume strain is equal to 0, and therefore the epsilon 3 would be equal to minus epsilon 3 by 2. So epsilon 3 is basically twice of epsilon 1 and 2. Now if you sum it up, you would see that it will come out to 0. And from there we get the relation between epsilon 1 and 3. And now if you put this also in von Mises criterion, so it is similar to the uniaxial condition, and there we know that the effective strain is equal to epsilon 1. So it will be similar here. Epsilon bar would be equal to epsilon 1. I'm sorry, it's not exactly the same as uniaxial condition, because here the third one is in compression in some sense, and the other two are in tensile condition. And therefore, if we look at the third one, which is, if it has to be equivalent to the third one as in uniaxial condition, then it will come out to 2 epsilon 1. And it will be advisable if you actually go through the steps, use the von Mises relation to get this value, and it will give you a hands-on experience on calculating these values. So you would get that epsilon bar is equal to 2 epsilon 1. Now using symmetry, we can apply the instability condition on any of the forces. Applied on any force or direction. So we have F1 equal to sigma 1 A1, and again we know that for instability dF1 it should be equal to, which is equal to sigma 1 dA1 plus A1 d sigma 1 equal to 0, and again rearranging, what we get is d sigma 1 by d by sigma 1 equal to minus dA1 by A1, and dA1 by A1 is equal to d epsilon 1, which we already know is equal to d epsilon bar by 2, and d sigma 1, which is same as the sigma bar. Therefore this can be written as or in other words, we can write d sigma bar by d epsilon bar is equal to sigma bar by 2. So for the biaxial loading condition, this is the relation that we get. And now if you put sigma bar equal to k epsilon to the power n, what you would get is epsilon bar is equal to 2n. So in this particular case, you would get a uniform elongation to a much larger strain values. This is what this relation is telling us. In fact, it will be twice of what you would get in uniaxial stress condition. So with this example, we will come to end of this particular topic, that is of plastic instability. Thank you.